Welcome to Wildcat Science with Mrs. Haugo. This is Advanced Science and we are in our water unit and we are studying why is water the basis of life, and this is part 2. We are starting back in on our fourth reason that water is the solvent of life, and when you're making a solution it is the solute or the thing you're putting it in and the solvent, which is the dissolving medium. So that's usually water. So a good way to remember the difference between solute, solvent, and solution is that you put the solute in the solvent to make a solution. And no other liquid can dissolve more substances than water. So all ionic compounds will dissolve in water. So table salt and any other of our ionic compounds will dissolve in water. And all polar compounds will dissolve in water. So if you remember, ionic compounds were one group and covalent compounds were another group that we talked about in Why is Water H2O? And then covalent compounds are broken up into polar and nonpolar. So basically, nonpolar covalent compounds are the only things that don't dissolve in water. So let's take a look, and this is an ionic compound. You can see because it has positive and negative ions, and it is dissolving in water. So the negative parts of it, the negative atoms, the negative ions, are breaking off and they are getting surrounded by the positive, the partially positive end of water, those hydrogen ends. And then our positive atoms, our positive ions, are getting surrounded by that partially negative side of our water molecule by the oxygen atoms. So this is how, let's say, table salt gets dissolved in water. So most chemical reactions that occur in organisms involve solutes dissolved in water. The term for something dissolved in water is an aqueous solution. So that term will come up again, aqueous solution. So let's do an example. Proteases are a type of enzyme and they are found in the cytoplasm of cells. If you remember, that's all the liquid part of the cell. And cytoplasm is mostly water, so we know that proteases are found in water. And the proteases connect with proteins, any protein that you eat, and it breaks them down into amino acids that your body can then use to make anything it needs. Maybe it needs amino acids to make some myosin fibers to make a new muscle, since you're working out so much and building muscle, or whatever it is that your body needs. Let's take a look at a picture. So you have a protein molecule that you ate, and then you have these proteases, which are enzymes, which you know are going to are their own protein that break down something. So you got your proteases, and they come and they break down that protein into its amino acids, and then your body absorbs those amino acids and brings it to the cell where it needs it. Let's say that arm cell, so you can make those myosin fibers for all your new muscle fibers. So another important chemical reaction that occurs in water in organisms is the calcium ions that are dissolved in water allow muscles to contract. So please write that down, and then let's look at a picture of it. Okay, so if you remember from biology, you have your myosin and actin fibers, and then calcium is going to come and sit here and open, like change the conformation. So then those myosin fibers can come up and bind to the actin, the binding site on the actin, and then it moves the actin and myosin past each other, and then that muscle fiber shortens, and then all your muscle fibers shorten, and then your muscle shortens and it contracts, and that's how you contract a muscle and move anything in your body. And that is because you have calcium ions dissolved in water. So it is good that we have water in our bodies, and it is good that we have water. The last concept we're going to talk about in our water, why is water the basis of life section is number 5, buffer solutions resist changes in pH. So we're going to talk about pH in water and buffer solutions. So buffer solutions are going to be aqueous solutions, and we know aqueous solutions are something dissolved in water. And also we know that organisms are sensitive to changes in pH. We are sensitive to changes in pH. One-celled organisms living in pond water are sensitive to pH. Dogs are sensitive to changes in pH. If you're alive, you're sensitive to things in changes in pH. And all aqueous solutions have a pH. And remember that organisms are predominantly water, and most biological reactions occur in aqueous solutions. So the pH of the solution where the biological reaction occurs is important, because if it's not the right pH, the organism will die. All right, so let's talk about the pH scale. It is the scale from 0 to 14. Anything from 1 or 0 to 6.5 are acidic solutions. And then 7 is going to be neutral, and pure water is neutral. It has a pH of 7. And then 7.5 to 14 are basic solutions. So pH, what is pH? pH is a measure of relative concentration of hydrogen ions, or more technically hydronium ions and hydroxide ions. So what does that mean? All right, so let's take a look at a picture, and I do want you to make this picture in your notes, please. So before we get into all the technical jargon, so pH is a measure of how acidic or basic something is. So on its most basic level or most general level, it's just a measure of how acidic or basic things are. But what does that mean? So you've got 2 water molecules here. And then what will happen in water is that this little hydrogen will go over here. This is called the dissociation of water, and this happens naturally at a certain concentration, at a certain rate. So this little hydrogen went over here, and then we were left with a hydroxide ion. And then this one has an extra hydrogen, and now it's H3O, and it is a hydronium ion, and sometimes you hear it referred to as a hydrogen ion. So because this little hydrogen, we know hydrogen is just the first element. It has 1 proton and 1 electron, no neutrons in it. And then when it leaves water, it was sharing an electron with water and with the oxygen, and the oxygen does not let it take its electron with it. So then it is, it's just basically a proton, so it's positively charged. So when this molecule lost a hydrogen, it lost a positive charge, so now this molecule is negative. And this one gained a positive charge, so now this one is positive. So what we're looking at pH is the concentration of these, of hydronium ions. So technically pH is the negative log of the concentration of hydronium ions. So please write that down, and then let's talk about what that is. So why don't you write down the formula, and then we'll talk about what it is. So pH equals negative log, and then brackets, hydronium ion, bracket. So concentration is how much of the solute is in the solution. So these brackets mean concentration. They actually mean molarity, but we're not going to get into that. If you took chemistry, you know what molarity, the molarity of a solution is, and how to calculate that. And then log is something we're just going to talk about quickly. That is a math function, and the log is the opposite of an exponent. So please write this down. The log function is the inverse of an exponential function. So what do we mean? So let's say we have 10 to the negative 1 exponent, and that's going to equal 0.1. Well, the opposite, or the inverse, I should say, is the log of 0.1 is going to equal -1. So looking at this in general, if we have 10 to the exponent of y equals x, then our exponent becomes our answer. The log of x is going to be y. So looking at this again, so 10 to the -1 was 0.1, so then the log of 0.1 is our exponent, -1. Okay, so you don't need to have that mastered, but let's take a look at pH. Okay, as I said before, pH is the negative log of the hydronium concentration, and so let's look at our pHs. So if we have a hydronium concentration in a liter of water that is 0.1, then we know that 0.1 is equal to 10 to the -1st, that those are the same thing. And we know that the log of 0.1 is going to be -1. So if we look here at our equation, the negative of -1 is 1. So our pH is going to be 1. So when we have a pH of 1, this is our hydronium concentration. And then if we have a pH of 2, this is our hydronium concentration. And you can see that this is 10 times less concentrated, so it's less acidic. And then we're becoming more and more neutral, less and less acidic. pH of 3 has 0.001, so it's 10 times as less acidic, or 100 times less acidic as a pH of 1. pH of 4 is tens, hundred, thousands, 10 thousandths, 1/10,000th, 100,000th. pH of 5 is 10 times less acidic. pH of 6 is 10 times less acidic. And then the pH of 7, the hydronium concentration is this, and that is considered neutral, neither acidic nor basic. And then we have 8, 9, 10. We would be adding a 0 each time until we get to something that is very basic, a pH of 14, and it has a very low concentration of hydronium, which if we come back to our drawing, if it has a very low concentration of this means it has a high concentration of hydroxides, and that's what makes something basic. So sodium hydroxide, soap, bleach, these are all basic things. Well, now that we've learned about pH, what does this have to do with living things? So please write this down. So remember, proteins, if you think back to biology, they are necessary for life. You can't live if you don't have proteins. Can't live without enzymes. If you remember, those are biological catalysts. They are proteins that do chemical reactions, speed up chemical reactions. And they only work in a specific ranges of pHs. So if you think back to biology when we did the lactase and lactose experiment, and that if we changed the pH, then the enzyme lactase would denature, and it wouldn't be the same shape, and if it's not the same shape, it can't do its job, and its job was to cut the sugar lactose into glucose and galactose. And we wanted that to happen so that the yeast could eat the glucose, and then the yeast made carbon dioxide and blew up the balloon. So if the pH isn't right, then the enzymes unfold, they denature, they don't do their job, and then you die. So that's bad. So I'm going to leave you at a cliffhanger. How do organisms prevent changes in pH if we know that changes in pH are bad? And we'll finish that up in our last video. I will see you then.